Hello, everyone. This is Shauna, and we're here for a video on section 8.4, hypothesis testing with proportions. So let me share my screen at this time. This hypothesis testing is very similar to the other hypothesis testing that we've been doing. There are a couple of discussion questions at the beginning of this homework, which I will be going over in a minute. But the main difference here is that our test value formula for proportion is different. And it can be potentially a little bit confusing. It's not something that we haven't dealt with and used. P hat is the sample proportion minus the population proportion over the square root of the quantity, the product of the population proportion times Q, the complement of the population proportion, divided by the sample size, okay? All under the square root sign. That's our main difference for how we get the test value. A couple of things that come up around this section and the next couple of sections that I wanted to point out, okay? Because historically, people have asked questions about this. So when we're doing hypothesis testing, okay, right now, where we are right now, with what we know right now, we only deal with one group. That's not going to be the case once we start chapter 9, but right now it is. When we talk about parameter, okay, or parameters of interest. Parameters, these are values that describe the population. We know that from chapter 1. So when she asks you, if the question is, what is the parameter, or identify the parameter, okay? Possible answers to this question are only 4, okay? So possible answers to this. Possible answers are mean, proportion, standard deviation, or variance. Okay, those are the ones that we cover. Now, the mean is mu, we know that. The proportion is p. The standard deviation is sigma. And the variance is sigma squared, okay? So every time you do a hypothesis test and the question is identify the parameter, or what is the parameter, it's one of these answers. Now, another question that I get from students when we do proportions is they remember doing the flow chart that we spent so much time on in 8.1 and 8.2, okay? And they're wondering why there's no flow chart for proportions. And the simple reason for that is there's only one test for proportions. So let me remind you, in section 8.2, which was our first section, this was hypothesis testing with sigma known, and that was a z-test, okay? Anytime you know sigma, regardless of what the sample size is, that's an automatic z. It's when we don't know sigma that we have some uncertainty, okay? Section 8.3 Section 8.3 was hypothesis testing with a t-test. Okay, with a t-test. And the flow chart comes these are both tests for means. This is a test for the population mean. And the other test, this is a test for the population mean also. Now, in the section where we are right now, section 8.4, this is hypothesis testing for proportions. And this is a population proportion is our parameter, okay? That's as far as we've gone. This is 8.4. 8.5 is going to discuss variance and standard deviation, okay? That's where we are. The reason we don't have a flow chart for 8.4 is we only have one test for population mean, for population proportions. We have two for means. The other thing I wanted to address is that in section 8.4, there are a couple of specific hypotheses. So let me stop sharing my screen at this time and share the PowerPoint slides here. Actually, let me share the book first. Let me share the book. So if you look at the homework, which we'll do in a minute, you're going to see that for section 8.4, it opens with some examples of what proportions are, okay? The format for a proportion statement is usually some percentage of some group do something. So once again, it's going to be something like this. It's going to be, if you're writing, so if I wanted to give you an example of proportions, okay? Examples of proportions. Generally, it's gonna follow the following format. So we're gonna have something like blank and then we're gonna have blank and then it's gonna be blank of some blank. Like there's gonna be another blank here, blank, blank, and then there's gonna be some action over here, okay? So there's gonna be some other blank over here. So for example, I'll show you what this looks like. So this is gonna follow the format of some percentage or ratio of some group of people or things take some action. That's generally how a proportion works. So for example, I could say 30%, and we don't have to make it true. We don't have to look these up. 30% of, let's say, Californians what action have they taken? Have been to Disneyland. That's an example of a proportion. Okay, a percentage or a ratio Or I could say something like 2 out of 3, because this is a ratio. 2 out of 3 women, let's say that's my group, 2 out of 3 women work outside the home, something like that. Okay, we're not looking at the validity of these, we're just looking at what you could do with this. Or maybe it's something like let's say like maybe you have 18% of all workers say they want to return to the office full time. Let's say that. I have no idea if these are true or not, but these are examples of proportions, and that's how you create it. A percentage or ratio of some group do something. That's how proportions are constructed. Okay. Now, let me stop sharing for a moment here. Stop sharing. Okay. Let me stop sharing, and I'm going to show you something. This is your homework assignment. Now, why did I just go through that explanation? Because if you look at, bear with me for a minute, having some trouble with the Zoom here. Let me go see where I'm at. Yeah. Okay. If you look at the question, on the first question on the homework, give 3 examples of proportions. Okay, there's examples in your book. I'll show you those. But I just gave you 3 more on this video. So there's no excuse for not answering this question. I told you how they were constructed. So if you want to create your own examples, you can. Okay, that's question 1. Question 2, when you are testing hypotheses by using proportions, what are the necessary requirements? Now, the reason I'm giving you this is if you go to her PowerPoints for this, she doesn't give them to you. And normally she does, but they aren't anywhere in here. Okay. There are several examples of how to solve hypothesis testing with proportions. She doesn't give you examples and she doesn't give you the assumptions. So I'm doing that for you here. I'm not going to go through the slides other than that, but I will go through the steps with you for the testing. So I just wanted you to see that and be aware of it. Here, she asks about the assumptions. So let me show you that. I'm going to stop sharing that. And I'm going to share the book. Let me bring up the, I don't think I have it open. Oh, maybe I do. Okay, here is the relevant material from your textbook. Okay, there are some examples here of proportions. If you look down below the paragraph where they give you the proportions, if you look here, it gives you the assumption. So let me read it for you. It says, a hypothesis test involving a population proportion can be considered as a binomial experiment. This is from chapter 5. Remember, binomial experiments are the ones that have only two possible outcomes, success and failure. Success means getting what we want to see happen. Failure means getting something different. When there are only two outcomes and the probability of success does not change from trial to trial. Recall from section 5.3 that the mean is mu equals NP and the standard deviation is sigma is equal to the square root of NPQ for the binomial distribution. Since the normal distribution can be used to approximate the binomial distribution, and where are my assumptions? Here they are. When n times p is greater than or equal to 5, and n times q is greater than or equal to 5, the standard normal distribution can be used to test hypotheses for proportions. Those are my assumptions. That's considered 2. So when I go back to the homework, okay, the next question, this is question 2 now. Question 2 says, when you're testing by using proportions, what are the necessary requirements? You have to have a binomial experiment. So let me write them in. You have to have a, and remember, it already is 1. It wouldn't be a proportion without that. This is a binomial experiment. You have to have independent trials. Independent trials. Okay, you have to have a fixed probability of success. Those are all underlying a binomial experiment. These are all underlying that. And the new one is that NP is greater than or equal to 5. Notice this is not 10, now it's 5. And NQ is greater than or equal to 5. Those are my assumptions. Because the first 3 on this list relate to binomial experiment anyway, she just added n times p is greater than or equal to 5 and n times q greater than or equal to 5. Now, we didn't come to the party for all that, as important as all that is. We came for the problems. So what I'm going to do here is I'm going to take a look at number 3 for you, because this is the one that gets people. I'm going to take a look at number 3, and we're hopefully going to do a couple of these problems. I'm going to stop the share for a second. Start it again here. Okay. Scroll up so we can see it. Now, in 2009, it says, I'm reading number 3 right now, 45.6%, there's my percentage of what? Motor vehicle accidents, what about them? Involved no improper driving. Okay, this is going to have a twist in it, which I only know because I've read the problem, but got to be a little careful here. Involved no improper driving. That means everybody drove the way they should have. Okay, so 45.6% of the people were driving the way they should have been. In an area comprised of 6 adjoining counties, it was found that out of 110 randomly selected accidents, 60. Now, be careful here. This says it involved improper driving. This is one of the few times we've seen this before. These are people who did not drive properly in some way. At the .10 level of significance, is there sufficient evidence to conclude, okay, now here to figure out my null hypothesis, I need to figure out what group they're talking about. So here, let me go to the blue one over here. Is there evidence to conclude that the proportion of accidents involving improper driving, remember, this percentage is no improper driving. So the percentage involving improper driving differs from the 2009 proportion, okay? So we have 2 groups. We have people who drove correctly and people who didn't. Now I want to show you something here. So when we, and I'm going to come back to this, when we go down to her keys, okay. Now, involves improper driving, okay? This mistake was perpetuated from the previous one, okay? Because we want to find that the proportion who involved improper driving, okay? So that's the deal. Okay, so in 2009, 45.6% of motor vehicle accidents involved no improper driving. Okay, so in this case, this is what we've got. This is a little bit tricky. So we have I'm going to get another whiteboard for this. Before we start the hypothesis test, I want to help you guys figure this out. So this percentage, 45.6%, is the proportion who did not drive improperly, didn't involve improper driving. That means that 100% minus 45.6%, which is a total of what is that? 44, no, 54.4% drove improperly. Okay. Okay, so if we pick up from where we left off, as I was saying, 45.6 is the percentage of people who drove correctly. They involved no improper driving, okay? The sample data, 60 out of 110, involved improper driving in some way, okay? Now, is there sufficient evidence to conclude that the proportion of accidents involving improper driving differs from the 2009 proportion? Well, in that case, here's what we have. We have to really be careful with this first. So these people, this 45.6, they did not drive improperly. These 54.4% drove improperly. And as far as your sample goes, the sample proportion, X is 60. Okay, I just wanted to make sure that we clarify this. This is and N here is 110. Now, this group, your P hat group over here, you have to be a little bit careful because this group, X over N, right? You have to be careful because is this X or not? Well, if you go to your page, it says that those people drove improperly. Okay, so this is in fact your X. Okay, this is your X. 60 out of 110 is your X. So 60 is your X, N is 110. Now, what does that mean for the way our hypothesis test looks? Here's what that means. When we set up this hypothesis test, we're going to set it up with this, and it doesn't specify to use the p-value method, so we're going to use the traditional method here. We're going to do this. We're going to say that when you set this up, you're going to say the parameter, as we discussed earlier, is the population proportion P. This is not P hat, remember. This is P because it's the population. So population proportion P, okay? The next thing you're going to do is you're going to state what the claim is, okay? Is there enough evidence to conclude that it differs from the population proportion? So differs, as you might remember, means that we're not equal to. So claim here is H1, and it's going to be P is not equal to, P is not equal to, and because we're looking at improper driving, we're going to look at 0.544. I'm going to change this percentage to a decimal. So this is going to be, P is not 0.544. 0.544, okay? Now, we're using the traditional approach. And once again, we're going to put in our givens, okay? So the given state, your given information here, you have to be a little bit careful. You need both of these, okay? But you also need this thing too. So your given information, your P is going to be 0.544. Your Q here is 1 minus P, okay, which is 0.456. So this is equal to 1 minus 0.544, and that's equal to 0.456, which is ironically what they gave you in the problem. They gave you the complement, 0.456. Okay. Now, you've got P, you've got Q, and let me put it underneath, actually, so it's less confusing here. Q is equal to that. Okay. Now your sample data here, these are the people who did not drive properly, okay? X here is 60 out of 110. This is your P hat. Okay, this is P hat. P hat here is going to be 60 out of 110. This is X over N. And that is equal to 60 out of 110. And that is if I work that out, then I'll come over here, share my handy dandy calculator. This is 60 out of 110. That's 0.5455. Okay, 5455. So here, this is this is equal to 0.5455. Okay, that's your sample proportion. That's P hat. Okay, that's your numerator. Okay, so that's all of my preliminaries. Now, step one here, I'm going to go to my actual hypothesis test now. Okay. Go to my actual hypothesis tests. So this is step one, my hypothesis test. So this is going to mean that I have HO. It's going to be P is equal to 0. Remember, it's the complement of 0.456. So that was 0.544. 544. Okay, so this is 0.544. Okay, that's my proportion. My H1 here is going to be P is not equal to that. So this is P is not equal, to 0.544. And 0.544. Now, that makes this the claim, and it makes this a two-tailed test. Because again, we have the not equal to two-tailed test. We don't need to worry about the statistical equivalent here because we already have the equal to. So we've got our pieces of step one. Now, we're doing the traditional approach. So in the traditional approach, the next thing we do is we find critical values. Okay. The critical values for this, we're going to have two of them. Our test value, we're only going to have one, but we always have two critical values if our test is two tails. They're going to be z-scores, and they're going to be the following. I usually use the positive and then just make it plus or minus. So z is equal to plus or minus and it's going to be the inverse norm. And the way that you get the right side, you do 1 minus alpha divided by 2. So here, z is going to equal plus or minus inverse norm of 1 minus 0.10 divided by 2. Because remember, my alpha was 0.10. So now when I go here and I say, let's look at our data. Let's look at our calculator here. So we're going to go to, I'm going to clear everything out. Okay. We're going to do a second distribution. Inverse norm should look very familiar. No special programs necessary. 1 minus 0.10. But we're dividing the 0.10 by 2. 0 and 1 is your alpha. I'm sorry, your mu and your sigma respectively. You get 1.645. Okay, 1.64 is your z. So now, remember we have two of them. So in this case, our z's are equal to, z is equal to negative 1.645 or 6.6445, and or z is equal to positive, right? Z is equal to 1.64 positive. Okay, that's my critical number. Now, my step 3 is going to be my test statistic, which is another place that on these problems you can get messed up because there's so many P's. Okay. So if you remember, let me take you back to something here. I'm going to show you the slides here. This is the formula that we want. P hat is going to be our sample proportion. That's the one that was 60 out of 110. Okay. P is going to be your hypothesized proportion. That's the one that we had to get. That's the 0.545. Okay. This P and this Q repeat from this, where this denominator ended. So in this case, we have the following. We're going to have we're going to go ahead. We're going to have P hat, which we know from the previous whiteboard, P hat is 0.5455. So we have 0.5455 minus my P hat. Now my P hat is going to be 0.456. I'm sorry, it's going to be, I take that back. It's going to be 0.544. Okay. The square root under here is going to be P, which is this is going to be 0.544, and then Q, which is 1 minus 0.544. And in here, my N is 110. So I'm going to calculate my Z. So I'm going to calculate that. I'm going to put it on the screen for us. I'm going to write it down off screen on a piece of paper first. Z is equal to 0.544, 1 minus my top is going to be 0.5455 minus 0.544. So it's going to look like this. We're going to do square root. Before we do that, we're going to say open parenthesis. Zero 0.5455 minus 0.544. That's the top. Now we're going to divide it by the bottom. Square root. Now, when you do the square root, you lead with the P, which is 0.544. Okay. If you remember, the complement to that was times zero 0.456. Okay. Divided by 110. Okay. These come from our population means and then our sample size. This answer is 0.0318 or 0.0316. So here, this is equal to 0.0316. So here we have this is equal to 0.0316 is my Z. Step 4 here is to for and I'll fix my box shortly. Okay, there's my box now. This is reject a show or do not reject a show. And this is where we draw the curve. So here you have the curve. There's my curve. Okay. Now, my task 0.0316. I've got some kind of gatekeeper over here. That's negative. Negative 1 point. Z is equal to 3V here is equal to negative 1.64. And on the other side, my critical value is equal to 1.64. Now, what are we saying here? Well, we're saying that, and I could even put a Z in here and say Z is equal to that. Now here we're saying Z is equal to 0.0316. So it's probably remember zeros in the middle. So 0.316 is going to be slightly here. Okay. This is where .0316 is. Now, what does that mean for us? Well, that means that we're in the non-critical or the non-rejection region. So what does that mean? That means we, remember this was the do not reject. Do not reject area because we're not in the tails, okay? Where our tails are over here. So we'd have to be over here. This is where we would have to be, but it's too small. So what does that mean? We do not reject the null hypothesis. So if we do not reject the null hypothesis, then we keep the null hypothesis, we retain it, and the claim is H1. So we can say that we can go here and say there is not, this is step 5 on our testing procedures. We can say that there is not enough evidence. And remember here that our claim was H1. So there's not enough evidence to support the claim at alpha equals 0.10. That's the proportion of drivers who drove improperly is different than it was in 2009. that's how this hypothesis test works. And that's the question that I wanted to show you here. Going to save these whiteboards for this particular meeting. And